Hey everyone, we're going to talk about linear regression today, and it's a rather involved subject, but it is not that hard to run in R. So let's dig in, and first of all, let's consider two numeric data sets, right? Correlation is a question of whether or not two numeric variables are related. So if we're going to look at them, let's look at the data vector x and the data vector y, both of which are numeric variables and have the same dimension. Then the deviation vector x is x minus the average, or x sub I minus the average of the x's, right? And the deviation vector in y is the y sub I minus the average, okay? And why do we do that? Well, it turns out that we can use these to determine the line of best fit, okay? So we think of a line generally as mx plus b, but in statistics, we usually do the line of best fit, which is y hat is the symbol. So that y hat equals the intercept a plus b times the variable x. And what are we trying to do? We're trying to fit this line to the data where the x's are plotted along the x-axis and the y's are plotted along the y-axis. In more advanced statistics, the regression coefficients are betas, beta sub 0 being the intercept, and then beta sub 1 being the slope of the first predictor variable. We can have more than one, so if we have another predictor variable, then beta sub 2 would be the slope of that one. Now, the key thing that I want to talk about is the residuals. Why? Well, the residual compares the predicted value, the one we get from the line of best fit, and the actual value, right? The value that was there. And so we just subtract, right? We take the data point minus its predicted value, right? And that's a residual. And the line of best fit is going to minimize the sum of the squares of all the residuals, right? So RSS, the residual sum of squares, right, is the summation of all the residuals squared. Awesome. Okay, and here's the formula for correlation. All right, and what we want to notice right away is that the denominators are closely related to standard deviations, right? So, right, we have the standard deviation is 1 over n minus 1 times the square root of what? And again, the stuff that's in here in the standard deviation formula is looking a whole lot like this, and I'll leave that there for the moment, right? Because we're going to do this proof pretty much in detail. Okay? And what does this mean? Oh, so the z-score, remember we talked about a z-score. The z-score is, right, y sub I minus the mean of the y values divided by the standard deviation, right? So we're really close to having this formula. And notice the n minus 1 out here. So it's clear that we're close, but we're not there yet. Let's verify this, okay? And here's all the work. The first thing we need to do is add a well-chosen 1, and you see it right here. The n minus 1 over n minus 1 equals 1, so multiplying by 1 doesn't change the value. And what are we doing? We're taking an n minus 1, which is also equal, right? N minus 1 equals 1 over 1 minus n minus 1. Right? If you think about, you flip the fraction down here and the n minus 1 is in the numerator, but that's the denominator of the big fraction. That's what we're doing. We're doing a little reciprocal property here. Why? Because I need the square root of n minus 1 here and the square root of n minus 1 here. So the square root of n minus 1 times the square root of n minus 1 is just n minus 1, and that's the n minus 1 up here. That has been transferred not just to the denominator, but the denominator of the denominator. Okay? And because it's split up, we can put one with the x's and one with the y's. Okay, now what we have is the standard deviation of x formula and the standard deviation of, oh, excuse me, we have enough that we have the z-scores, sorry. We have the z-score formula, and let's pull it out. What are we doing? We're splitting it right here, right? So that the first half is here times the second half. Now, these are all products. All these terms inside are products. So since they're being multiplied by each other, I can pull them apart, right? And put them here. Now, the summations are a little bit of a concern, but I'm going to gloss over that particular piece of theory right now. Why? Because now we're getting so close, right? We have the z-score formula for the y's and the z-score formula for the x's, and I drop some parentheses out, and you see that we have in fact verified the formula that the correlation R is equal to 1 over n times the summation of the z-score for x and times the z-score for y for all the pairs x and y. So that's the basic stats proof, but it turns out that the correlation coefficient is a cosine. All right, why? Well, where theta is the angle of incidence between the vectors. Okay, so we're jumping back right to a Calc 3 physics formula that a lot of people learned, that U dot V, again, thinking of the deviation vectors, right? But U dot V is equal to the magnitude of U times the magnitude of V times the cosine of the angle of the incidence between them. And we apply this formula, or we plug in the deviation vectors into this formula, and we see that the magnitude of the deviations in x times the magnitude in deviations in y times the cosine of the angle of incidence between them is equal to this dot product. Okay? And when we just write out what these expressions mean, what do we end up with? We end up with the formula we were just working on in the previous slide, which was equal to R. So what do we find? We find that R is equal to the cosine theta. All right. Why do we care? Well, cosine theta is great. Why? Let me just, for the moment, say yes. Why? Well, think of the cosine. If the two angles point in nearly the same direction, the cosine of theta is going to be the cosine of something close to 0, right? The vectors are pointing in the same direction, so the angle of incidence is small, close to 0. What's the cosine of 0? Oh, the cosine of 0, right, is 1. Right, we're going to have a really strong correlation when the vectors are pointing in the same direction. And okay, what is the cosine when the angles are pointing nearly in opposite directions, right? If they're almost in opposite directions, then the degree measure of that angle of incidence is about 180. The cosine of pi, or the cosine of 180 degrees, is about -1. Okay, so there you see, right, if they're pointing in exactly the same direction, the cosine is 1, and the correlation is perfect. The correlation equals 1. And when the cosine is 180 degrees, the cosine of 180 degrees is -1. So when they're pointing in opposite directions, the cosine is perfect, but negative, right? And then what about when they're at right angles? Well, the cosine of 90 degrees is 0. When they're at right angles, they're independent of each other and don't have any correlation whatsoever. So it's a really nice formulation of the cosine, of the correlation, that it's a cosine, and helps me remember that, how everything works, what the interpretation is. So in statistics, we say that R is a unitless quantity, and that's true. It is a strength of correlation. All right. And this is a summary of what I just said about how the vectors point in the same direction or they don't. So there it's written out and you can see a little more. Okay. And what happens when we add a constant to each component of x? Right, so this is adding a constant to each component of x. Well, it just increases the mean by x, right? Each of the values in the data set gets k added to it. So I'm taking the mean with k added to each number, and then so you can do that formula yourself. It's not that important. The standard deviation doesn't change at all. Why? Because the dispersion of the items is still the same. We've just shifted them all along the x-axis by k units, either left k units or right k units. So it hasn't changed. And I do go through, add a little context there, put in the z-score formula, right, which gets used a lot. And what are we saying? We're saying that the z-score doesn't change when I add k to every unit, which is interesting. It's something to consider. Okay, so here's an example of the quarter and real wages increasing, right? That's what we'd like to look at. So we've got this example data. And let's just do this. So a calculus approach, and again, we do hopefully know calculus, but let's just say these are formulas we know that the slope of the line of best fit is r times the standard deviation in y over the standard deviation x. I think I may have these switched. And the intercept is equal to the average y value minus the slope times the average x value. All right, and then r and r squared we can calculate from the regression. Okay, and so what do we have? We have beta estimating the slope. We have alpha, excuse me, an estimate of the slope beta, right? We have estimates of the slope alpha, and we're trying to estimate the population regression rho. So this is the Greek letter rho. It looks like a P, but it's actually a Greek letter rho, which is an R. And so what are we trying to do? Well, this is calculus, right? So I'm trying to minimize the residual sum of squares. So if I just write out what the residual sum of squares is in function notation, right? I have the sum of the squared residuals. And what are we doing here? We're substituting in, right? That that is the line of best fit applied to x sub I, right? With the slope a and the intercept b. All right, so let's go forward just a little bit. Okay, and in calculus, if we're doing minimization, what do? We take the derivative and set it equal to 0. Here, we take the derivative of the function with respect to the variable a, and get this, and we take the derivative with respect to the variable b and get this. We set them both equal to 0, and we solve. Okay, and what's the second derivative test doing? It's showing that we'll have a minimum, right? That if the second derivative is positive for both, right, that means it's concave up, and therefore the point that we find will be a minimum. All right, and sorry, I keep getting rid of this. Right, so as we simplify the derivative with respect to a, right, and then divide through by -2, but 0 divided by -2 is still 0. Then I can split the summations. And NA, right, this is just the summation of A, n times, right, the sample size times. So NA equals these two, right? We subtract them over to the other side and then divide through by A. Oh, and that's interesting. Why? Because this is the average of the y values, and this is the average of the x values inside the parentheses, right? So we have verified that formula, and I'm getting rid of the stray marks so that we can take a look at solving for b. We do the same thing. Take the derivative, set it equal to 0, right? And what's going on here, right? Well, what we know is that A is equal to this. So you can see the stuff in red, right, is equal to A, and we substitute it in. Why? Because we have two equations and one equation and two unknowns here, right? So we're getting rid of the A by substituting in what A is equal to here. So now we have A in terms of B. This is fine. We can gather our terms and our summations into this form. Okay. And why do we do that? Well, if I can get rid of these stray marks, right? So we're adding a well-chosen 0. Why? Well, because this is going to allow us to recombine. Why? Because I can factor out the y bar, okay? And then this is just, well, I'm sorry. And then this is just equal to x bar, right? So this is y bar, x bar. All right. And then putting all the summations together. And I end up here. Okay. And we're taking this value, right, and doing more algebra. And we multiply by a well-chosen 1, which is rather ugly, but you will agree to what I just put in the red rectangle is in fact equal to 1. And then we're grouping the terms slightly differently. Why? So that I have it in exactly the formation that I need it. It is the correlation times standard deviation of y over the standard deviation of x. And this, here it is correct. I had the reciprocal of that in the slide before, and I apologize. Okay, so that was quickly through some proofs and proofs about regression, but why? Okay, let's talk about what we should learn. The line of best fit always goes through the point x bar, y bar. So it goes through the average of the x's. That's the x value, or excuse me, for one point on the line of x of the line of best fit, we have x bar, comma y bar. Average of x, comma average of y. Okay, and we know that the correlation and slope are related very closely. Why? S sub y and S sub x are both standard deviations which are positive or 0. 0 doesn't make much sense, but they're positive or 0. So what does that mean? That means if the slope of the line of best fit is increasing, then R is positive. And if the slope of the line of best fit is decreasing, then R is negative, right? So if the slope of the line of best fit is positive, we have a positive correlation. And if the slope of the line of best fit is negative, we have a negative correlation. We can actually calculate R from B and B from R if we know the standard deviations. But I just showed you how R and B must always have the same sign. And here is the standard hypothesis, which we will look at more in a moment. You can look at the least squares approach. This is how in linear algebra we do it. Um, and so you have to know what the least squares solution is in linear algebra, and it comes down to the fact that it's a projection. We project, and we know this is consistent. This system of equations is consistent. Therefore, there exists a projection, i.e. a least squares solution, which is what? Well, it's the orthogonal projection. All right, and you can slow down the slides and look at this. This does make sense if you've had linear algebra. And these are called the normal equations. Excuse me, these are the normal equations for that projection or the line of best fit. Okay, and I'm not going to go through I'm going to go through this quickly. Why? Well, it's not the most important material. This is helping you understand the theory. Okay, but remember, we're comparing predicted versus observed, right? And if they lie on the line of best fit, then we know this is true. This is called the design matrix. The vector v are just the coefficients a and b, the slope and intercept, right? And y, the y vector, that's just the data vector in y. So here, this matrix, design matrix, just gets a column of ones inserted before the x's, the numbers. X is a numeric variable. And what happens is I end up with a very simple matrix equation that I can solve, right? I can solve x transpose x, and I can calculate x transpose y, and as long as x transpose x is invertible, then I can solve this equation. But we know that x transpose x is always invertible. Okay, and then we have a calculation of a and b. Okay, well, that was interesting. That's how a lot of computers do it. They do it with the linear algebra because it's just calculations. There's no setting things equal to zero, solving, simplifying. It's pretty straightforward. All right. And again, some more details. This is making the point that we are doing an orthogonal projection. And it is interesting that every linear regression problem allows an orthogonal design matrix. Why? Well, that means it will have a unique solution, a unique answer. And this is doing it with the projections. Notice that the slope is the same and the intercept is different. So we have a method that's parallel and allows us to calculate things with projections. Again, most computers, I think, do it with just the straightforward linear algebra. So let's do an example. Okay, so our hypothesis, what does this mean? Okay, it means rho, right, is an estimate of r, or r is an estimate of rho, I should say, right? So we calculate the sample statistic r, and we're trying to estimate the parameter rho, or the correlation between the two variables. And the null hypothesis is there's no correlation at all. There's zero correlation. Then there is some significant correlation between the two. And sometimes we can guess whether it's less or greater depending on how much information we have from prior research. But this one usually works. Why? Well, because we calculate R, and then R is going to tell us whether there's a positive or negative correlation. So part of the output that we'll get is R. Okay, so what are we going to do? We're going to create the model. So we're using MOD as a variable name. We're using the function linear model, LM. Now, we're using MPG versus display, DISP. What is this? Well, miles per gallon for a car you're aware of. Displacement measures how much fuel-air mixture it can draw in, the engine can draw in on each cycle. So again, bigger displacement, it gets more air and fuel into the engine. It burns more of that mixture. every time. All right, so maybe there is a correlation or a connection between miles per gallon and displacement. Again, bigger engines with larger displacement are more powerful. Why? Just because they have more explosions and bigger explosions going on in the engine driving those pistons. Okay, so after we create the model, we're going to create a scatter plot with a line of best fit superimposed on it. We're going to do our data verifications, which is what we have to determine whether or not the residuals are approximately normally distributed. And if they are not, the data are not appropriate for regression, then we're going to run the regression and report out. Okay, and our first example is this miles per gallon versus displacement. And it's in MT cars, which is a data set that's provided in native R. Okay, there are 3 or 4 data sets in native R, and this is one of them. So we don't have to do any work to import that data into R. Sorry, so there's example 1. Let's jump into the Data Hub notebook. Right, and this will load the data for later examples, automobile example. And what am I doing? Right, the very first thing is we're loading the model using linear model, lowercase mpg tilde disp, and the data equals mt cars. Okay, so next we're going to do a scatter plot with the line of best fit, and notice that I can just copy paste this out of right here, right? This is the exact same thing as we created the model with. We can't plot the model, it'll plot something different. So we have to type this again or copy paste it from above. Now AB line from the model, what does that do? It goes and grabs the line of best fit from the model. Okay, it's going to draw that line with a line width equal to 3 in the color of blue. So the line of best fit is going to be superimposed in blue on top of the scatter plot. And there we go. Okay, so what do I need to remember here? The very first thing I do, I have to create the model using this statistical formula. I put a tilde between the 2 numeric variables, and R will figure that out. Okay, then I plot that linear model. Just plot. Plot will do the scatter plot on this statistical formula. And then I use AB line on the mod. And again, these are options. The LWD equals 3 is an option. I don't have to use these options. It will run fine without the options. I prefer them. Just to really highlight the line of best fit. This is a really strong correlation. On weaker correlations, highlighting the line of best fit is really helpful because the graph can get busy. Okay, now let's take a look. Is this a linear relationship? And we have some outliers here that don't really fit the model. This is starting to get far away. Okay, so we have 5 or 6 outliers, but generally speaking, we have a cloud of points in what appears to be a reasonably linear relationship, okay? And I will admit that these up here aren't thrilling me. But let's go ahead and run the diagnostics on this. Okay, so the data verification, remember, we're going to inspect a QQ plot and a density plot of the residuals. Let's talk about that, how that goes. Again, we're using layout matrix. C1, 2, ncol equals 2. 8 or 9 is usually the right LCM. And here we go, QQ norm model $sign residuals. So the model does have data frame output, and $sign residuals is getting me that, that column. Okay. And then I'm plotting the QQ line. Why? Well, okay, so what are QQ plots? QQ plots are plots that if the data, a QQ normal plot is, if the data is normal, it plots along a perfectly linear, it plots along a line. Okay, so what we're looking for here is for the data to be really, really close to the line. Okay, and you can see that we do really well down here. But at the top, we're a little further away from the line than we would prefer to be. And at the bottom, we're also starting to trend away from the line further than we would like to be. And you can see in the density plot why there's just a longer tail to the right, so there's more outliers to the right. And you're going to ask me, well, is this data appropriate for regression? And I'm going to say barely. Okay, I do see some serious problems, especially up here. Those points are too far away from the uh, line, from the QQ line. So what am I going to say here for my data verification? Going to say the QQ plot of the residuals shows several outliers to the right, and the density plot is skewed right. Let me switch that to markdown cell. Okay. And is that all I'm going to say about it? No, I'm going to say that we may conduct a linear regression, but will be concerned about its accuracy. Okay, so I'm going to finish the example. Normally speaking, I'd say, ooh, this is just too bad. I'm going to stop and not run a linear regression at all here. For the sake of having an example so that you have all of the commands, I'm going to go ahead and run it. I will admit that perhaps we probably shouldn't run it. Okay, what am I doing here? With the cat variable, I'm creating r equals, right? That's just text. And then I'm doing the correlation of these two data vectors, all right? So COR is the correlation. What am I doing here? Why? Well, you'll see in a second that the regression, which I get when I do the summary mod, all that output lets me know the regression parameters. It doesn't really tell me R. It tells me multiple R squared and adjusted R squared, and it gives me a p-value, which matches this p-value in the model up here, but it doesn't actually tell me what R is equal to. Okay, so what am I going to do? I am going to just, include the correlation in a cat statement above, so I have it, and saves me from calculating it later. And what am I going to do here with the reporting out? Okay. We have a strong negative correlation between MPG and displacement because R equals negative 0.847. Let's just do 848. And P is equal to 9.38. I'm going to use a backslash times and then 10 raised to the open close curly brackets. Why? Because that negative 10th is going to display funny if I don't. So let me switch this to markdown and let you see what I've got so far. We have a strong negative correlation between the two variables because the correlation coefficient was calculated to be negative 8.48, and the p-value is much less than alpha, right? Which is less than, sorry, 0.05, which equals backslash alpha. Okay, and you notice that I said strong. Okay, so let me just throw this in, strength of correlation. And I use the 25s, okay? Why I say that if R is less than 0.025, and let me do absolute value, okay? So absolute value of R is less than 0.025. We have little or no correlation. And I'm going to move up if the absolute value of R is between 0.025. So let's see, that's going to be LEQ for less than or equal to up to 0.50. Sorry, what did I do wrong there? That one's interesting. Somehow I got bumped out of markdown mode. There we go. We have weak correlation, okay? So between 0.25 and 0.05, we have weak correlation, okay? And then I'm going to move up to 0.5 to 0.75. So I copy paste there. I'm going to switch to 0.5 up through 0.75, okay, where we have moderate correlation. And then for the last one, right, I'm going to have strong correlation, and I'm going to get in there and do a greater than 0.75. And you'll probably notice that the inequalities don't work out perfectly. I should have an or equal to here or here. But this is a sliding scale and a judgment call anyway. If you want, you can put in the GEQ for greater than or equal to. And then that would make the inequalities work out. But what am I saying? I'm saying this is how I know whether to say strong or weak. Oh, by the way, the red here means that I have mistyped the word alpha. Okay, so this is how I'm coming up with the word strong correlation. Negative is obvious because it's right here. Okay, I have a strong negative correlation. And it's significant correlation. Why? Because the p-value was less than 0.05, which is alpha. Okay, so that's the reporting out. And again, this is the strength of correlation that we're going to use. All right, so let's do another one. And the first thing I want to do is the hypothesis. What hypothesis are we testing? We're testing in the perf. That should be pers, right? The personality data set that the variables thrill and OPT are correlated. Okay, so that hypothesis goes down pretty easy. H subscript 0 colon, and we're doing rho equals 0, backslash rho equals 0, and make that markdown. And you'll see that we get the symbols we want out of the $ mathematics. Okay, and I'm going to copy paste. Why? Because this is, I'm going to use NEQ for not equal to. As you saw, we learn the sign of the regression coefficient as we do the calculations, so we're golden, okay? So there's our hypothesis, and we want to do a scatter plot. So remember, we're going to do a plot of this but we're going to do the statistical formula thrill.opt, okay, and we're going to do data equals parse, okay? And that works out great, but what's the problem? We don't have the line of best fit superimposed on it. So what are we going to do to fix that, right? If you remember, what we want is we want to create a model, and I'll call it mod 2. So the second model we've created is going to be LM parentheses, and it's the same thing. It goes in the plot, right? So mod 2. All right, then we're going to do plot, and then I'm going to do AB line from mod 2. And again, I prefer the line width equals 3, and you can do whatever color you'd like. Sorry, color equals, how about red? Color is not a graphical parameter. So col equals red. I'm sorry, a couple of other languages that I program in use this. You can use green, whatever you'd like to use. I'll go back to blue. I do like blue. And you can see that this, if I didn't have the line width cranked up, this can be kind of busy. What's going on here? Well, the optimism values are along the x-axis. You can see generally as they increase, right, the thrill-seeking scores increase. So a more optimistic person tends to do more thrill-seeking behaviors. All right, but let's note that if this line of best fit has zero slope, if it's perfectly horizontal, parallel to the x-axis, that would be zero correlation, right? Zero slope means there's no correlation. Now, that's clearly not what we have, but we don't have a very strong slope here. We do have some positive slope. So this is why we're going to go ahead and do this, right? We're going to test this with the hypothesis, with the linear regression, but we don't know if there's any correlation here. It might be weak, okay? So we need to do the data verification. How does the data verification work? Well, remember, we're doing the residuals, okay? And we are doing, actually, let me copy paste it because it is the same thing every time. And this will save us a bunch of time if we copy paste it from above. What are we doing? This is the layout to get them side by side. And notice we're doing plot equals. Why? Because inside the parenthesis counts as one plot, which is going to be one space in our layout. But there's actually two things here. I first use QQ norm to make the QQ plot, and then I use QQ line, right, to superimpose the line of best fit on it. Okay, so this is going to be a QQ plot of the residuals. This is also going to be a density plot, except, right, I need to be doing mod 2 instead of just the model. Okay, and that'll work with the current data. All right. Let me just open this up. Why? Because this I meant to be a markdown cell just so we can set off, what's happening neatly and nicely. And okay, so what do we have here? Okay, from here down to here, this data is absolutely great. And we notice that it deviates away from the line down here for 7 or 8 points down there and for 3 or 4 points up here. This is not bad. This is okay, right? We're going to say that this QQ plot turned out okay, but it has heavy tails. Okay, what does heavy tails mean? It means that these residuals as a normal distribution has more outliers to the left and to the right than we would suspect a regular normal distribution would have. Okay, so the tails are a bit heavy, but otherwise we have a very bell-shaped distribution. We get confirmation of the bell shape from the density plot. So we're going check, check. This works out. All right, our data verification. Data verification, markdown, right? So these data are appropriate for regression procedures because the QQ plot is linear but shows heavy tails, and the density plot shows an approximate bell shape. Okay. And again, noting the heavy tails, is that going to cause a great deal of inaccuracy? No. It's not going to cause a great deal, but there is a little bit of inaccuracy that's going to pop in there. Okay, and I guess you heard my phone there, and I apologize for that. Let me add a couple more spaces in here. Why? Because now we're going to run this regression, and it's a linear regression. All right. And what do we do to run the regression? What we want to do is summary of mod 2, right, which prints out everything. But what we've been adding in, or what I tend to add in, is I add in the cat r equals, and I want to know this value, right? And I get that value by doing core of what? Well, I have to do purse dot thrill, comma purse $, not dot, but $, OPT. And that just prints out the correlation coefficient. And notice that it's slightly higher than 0.25. And if you remember the strength of correlation chart that I just put in, right, that's going to count as weak positive correlation. So that's going to be in my reporting out. I am going to say, right, we find a weak positive correlation of R equals, and now I have to scroll back up enough to see it, 0.3, let's just call it 0.3. I'll do 0.3, that's easier, 0.3004. We find a weak positive correlation, which is significant because, right, the p-value, right? So now I'm looking at this p-value, which also matches the p-value in the model, as you'll notice. So the slope is significant, and also the intercept is significant. So it's the R is testing both parameters in the line of best fit, and they both turn out to be significant, although the correlation goes along with the slope. That's why we're using the 0.0. That's why we're using p equals, oh, sorry, lowercase p equals 0.0, 1, 2, 3 zeros, 5, 4, 2, 1, which is less than 0.05, which equals \alpha. Okay, put that in Markdown. Okay, and this is our reporting out. Sorry, I should have mentioned that. So our reporting out, we find a weak positive correlation of R equals 0.3, which is significant because of the p-value. Which indicated rejecting the null. All right, so we did reject the null hypothesis, which gives us evidence that there is a significant correlation. Why? Well, because p was less than 0.05. All right, so we have a weak positive correlation because of the R value, which was significant because of the p-value compared to alpha. which indicated rejecting the null. And then what I'm going to do, I'm just going to say one sentence. Thus, we find that optimism and thrill-seeking behaviors are significantly and positively correlated. Okay, so this last sentence just kind of wrapping it all up in terms of the research that we did. This is kind of amusing. Why are thrill-seeking behaviors and optimism correlated? Is that because people are optimistic about making it through the thrill-seeking successfully with no injuries? I don't know. It's one of these things that has always been pretty amusing to me. But there you go, reporting out. And then gestational days versus birth weight. Okay, so we're going to do the same thing, only this time I'm going to call it mod 3. Right, and what is the model we're making? We are doing gestational dot days tilde birth dot weight, which makes sense. Gestational days, the number of days, the length of the pregnancy in days, and birth weight, and babies that are in gestation for longer periods of time, way more. We know this because 8 months of gestation, the baby is much bigger than at 2 months of gestation, right? So there is a growth that happens, and we would think that more days would lead to a higher birth weight. And this data is is it births or baby? I think it's births. Let's see if that works. It does not throw any errors at us. Okay, and let me call this mod 3. This will be model 3. And so what are we going to do? We're going to do plot. Again, the same thing. We're going to plot this. And we're going to do AB line of mod 3 to get this superimposed. The line of best fit will be superimposed. And let's say the color equals blue. Okay, so, and then the line width might even need to be a little bigger here just because you can't even really see it. This cloud of points is so dark. So is there a correlation here? Yes, the cloud of points is very dense, close to the line of best fit, right? Are there some outliers? Yeah, there are some outliers. We don't love the outliers, but this is a pretty strong correlation, at least visually. This does bear do this suggests we should do the regression and see what's going on here. But let's definitely do the data checks. And by the way, the hypothesis is the same here. Okay, so jumping in with some data checks. Data verification. How does that go? Well, remember, we're trying to do the residual plot, right? And we're doing the density of the residuals and the QQ line of the residuals. I'm going to grab this again from here. We've talked through it a couple of times already, but what are we doing? Okay, so the layout matrix is pretty standard. This plot, so the curly brackets enclose the plot. This semicolon separates the two pieces of the plot. The first piece of the plot is the QQ norm function, and the second piece of the plot is the QQ line function. And again, mod 3 to get the model 3 residuals put into that plot. Then we're going to do a density plot on the mod 3 $ residuals. And what do we get? Whoa, my goodness. Okay. What did I see? I saw this and went, wow. Okay. Those aren't just heavy tails. Those are crazy heavy tails. Way more outliers, both above and below in this plot than we want to see. This is horrendous. Okay. And I just can't do it. The other one was borderline, and you might argue that we could do it as long as we were careful about the accuracy. But no, 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 no. This is a problem. Okay. And again, what's the problem? These outliers, right? The outliers actually cause a major problem with regression, and we need these data points to fall much closer in towards the blue line, the line of best fit. And those curved lines I just drew, we need the data mostly in there. A few data points outside of that wouldn't kill the regression, but we've got so many data points that are outliers that this is just absolutely no, 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 no. This failed data verification. So let me type that in, right? So I'm going to, these data are not, let me yell with all caps there, these data are not appropriate for linear regression procedures due to the fact the QQ line veers so far. Wait, how about this? The QQ plot veers so far from a straight line. Okay, so my point here is that it can veer a little bit. I mean, we don't mind it. Let's see. So, and this is kind of reporting out at the moment. Um, these data are not appropriate for linear regression due to the fact that the QQ plot veers so far. Or how about the points in the QQ plot veers so far from a straight line? Thus, we will not conduct a linear regression. Why? Well, because linear regression is not appropriate. So remember, in statistics, the computer will take in any data you give it and do what it can with it, right? And if it can produce the results, it will. But if they're gibberish because of a, residual plot that is clearly not normal, that's not just heavy tails, that's just wacky, crazy outliers, to the point that it's just going to ruin all the accuracy that we would hope to have. All right, so the results for example 3 is no, I'm not running this at all because the data are not appropriate for regression. And you will get 4 full points on a test for doing the right thing based on the data verification. So be very careful with your data verification.